Hello everyone, welcome back to Math with Amala. This is the part 6 of grade 12, chapter 1 Relations and Functions. So far we have discussed relations and functions and their types also. Here we are going to start the examples 7 till 14. First one, example number 7. Let A be the set of all 50 students of class 10 in a school. Let f from A to n be function defined by f of x equal to roll number of the student x. Show that f is 1 1 but not on 2. Here we can define two sets. A, the set of all students. There are 50 students in total, and you can give their names in the first set, and in the next set it is the natural number set which contains the numbers from starting from 1 towards the infinity. So it will contain 1 to the numbers from 1 to 1 to 50, and then it again contains 51, 52, 53, etc. Towards the positive infinity. So for each name, you can give some numbers from the natural number set. That is, for example, let's take Amal for first one. Then, like that, you can give different roll numbers in the order for each. Hence, the function is f of a particular student is equal to roll number of that student. So let's take f of Arun or f of Midun, which is equal to 23. Or else we can give some other names, f of Nila equal to 25, or f of Amal is equal to 1. Like that you can give different. So there is a chance for one student to hold only one roll number. No two different students of the class can have same roll number. Okay, therefore f must be 1 1. For each student there is a particular number on the next set. Hence it is 1 1. We can assume without any loss of generality that roll numbers of the students are from 1 to 50. This implies that 51 in n is not roll number of any student of the class. So that 51 cannot be the image of any element of x under f. Hence f is not onto. As I have discussed already, there are numbers which are going even after 50. 51, 52, 53. But there are no students in the first set. Hence it is not onto. Next one, example number 8, show that the function f from n to n given by f of x equal to 2x is 1 1 but not onto. Here n is containing numbers from 1 to infinity. Both sets contain the same. So f of 2 is equal to 2 into 2, that is 4. F of 5 is equal to 2 into 5, that is 10. F of x equal to 2x. Hence each element in the first set is having a particular element in the next set, but the reverse is not true. Let us consider a number 1 from the codomain set, that is the second set. In order to get a 1 in the y place, or f of x equal to something, you have to write like 2 into 1 by 2 equal to 1. But 1 by 2 is not there in capital N or natural number set. Hence it is not onto. Prove that the function f from R to R given by f of x equal to 2x is 1 1 and onto. Let us prove this just through the definition itself. Let us suppose f of x1 equal to f of x2. That means 2x1 equal to 2x2. Here the domain and codomain are different from the example number 8. This implies x1 equal to x2. We can cancel the 2's. You will get x1 equal to x2. And it is already given that for any real number y in R, there exists y by 2. In the previous case, we were not having 1 by 2 in the in a natural number set. But here in R, we have 1 by 2. And so you can write 2 into 1 by 2 into y. That's equal to y. So f of y by 2 is a given number. That's equal to 2. You can write like it is an onto function. Example number 10, show that the function f from n to n given by f of 1 equal to f of 2 equal to 1 and f of x equal to x minus 1 for every x greater than 2 is onto but not 1 1. Here f of 1 and f of 2 are equal and their value is equal to 1. That means the numbers or the elements 1 and 2 are mapping to the same image 1. Now itself it is clear that it is not 1 1 because we need different values for different elements from the domain. This implies 1 not equal to 2, which is a true case. Now we can write it is not 1 1. This is enough in order to show that it is not 1 1, and we don't want to go for further and values of x which are greater than 2. The next case is about onto or the surjectiveness. Let's take the codomain set where y not equal to 1, then f of x equal to x minus 1 is the value or the function, then y is equal to x minus 1. So f of y plus 1 will be equal to y plus 1 minus 1, that's equal to y. Thus we can say that f of y plus 1 equal to y means it is an onto function. It has a proper pre-image. Thus we can say that it's an onto function but not 1 1. Now let's say for 1 belongs to n also. Here we can see that f of 1 is equal to 1. By this reason also we can say it is an onto function. Example number 11, show that the function f from R to R defined by f of x equal to x square is neither 1 1 nor onto. Here f of minus 1 and f of 1 are 1. They are moving to the same value 1, hence it is not 1 1. Also the element minus 2 in the codomain. If we take minus 2 in the codomain set, then it is not having a particular element on the domain R. Therefore it is not onto. Now let's move to the example number 12. Show that f from n to n given by f of x equal to x plus 1 if x is odd, x minus 1 if x is even. Here, suppose f of x1 equal to f of x2. In order to prove the 1 1 property, you can take f of x1 equal to f of x2. Here x1 is odd and x2 is even. Then we will have x1 plus 1 is equal to x2 minus 1, that is x1 minus x2 equal to 2, which is impossible because one is odd and the other is even. The next case can be x1 is even and x2 also is even. Here x1 minus 1 and x2 minus 1 they are equal. Then x1 minus x2 is equal to minus 1 plus 1, that is 0, which implies x1 equal to x2. Hence it is 1 1. Hence the even cases are holding the property 1 1. Now let's take x1 odd and x2 odd. Both are odd. Here you will get x1 plus 1 is equal to x2 plus 1. x1 minus x2 equal to 1 minus 1. Again x1 is equal to x2. Here this is also 1 1. To prove the onto property, let's take 2r plus 1 in the codomain n, then 2r plus 2, that is if it is odd f of r plus 2r plus 2 is equal to 2r plus 2 minus 1, that is 2r plus 1. This will be in the domain set. And then for the even numbers, there will be a 2r in the codomain. For f of 2r minus 1 is equal to 2r minus 1 plus 1, that is equal to 2r. So 2r minus 1 is in the domain set. Hence it is an onto function. For every number or element in the codomain set, there is a pre-image in the domain set. Example number 13. Show that an onto function f from 1 2 3 to 1 2 3 is always 1 1. So let's suppose f is not 1 1. We have to prove it like 1 1. So let's arrive at a contradiction. Let's take in the first beginning itself, suppose f is not 1 1. Then there exist two elements, say 1 and 2 in the domain. Because 1 is moving to 1, 2 is moving to the same 1 itself, and 3 is moving to 2. Hence the range of element will be, the set will contain only two elements 1 and 2, but actually that complete set contains three elements 1, 2 and 3. This indicates the particular number 3 on the codomain set is not having a pre-image on the domain set. Hence it is not onto. This is a contradiction actually for the onto property. Hence it should be a 1 1. Because we have assumed it like not 1 1. Hence we can say that it is a 1 1 because we have a remark that onto functions are always 1 1. Next example number 14, show that a 1 1 function f from 1 2 3 to 1 2 3 must be onto. Since f is 1 1, it is given f is 1 1. Then the three elements 1, 2, 3 must be taken to three different elements of the codomain 1, 2, 3 under F. Hence F has to be onto. Hence the to and fro condition is satisfied here. There is a particular remark that for the finite set 1 1 function implies onto, and also onto map implies 1 1, but it is not the case of infinite sets, because it is not necessary that this characteristic should be held in between infinite set. Go through these portions once again and clear your doubts through comments. Please be stay tuned for the next video.